Assalamualaikum respected teachers. We are from group 3. This is a project presentation for EEE 318 Control Systems Laboratory. Our project is object balancing on a beam using PID Controller. I'm Saba Kamal Orni. My ID is 2006009. Here is a short introduction to our project. This project presents the design and implementation of a control system for a car and beam balancing mechanism. Using a closed loop feedback structure, the system maintains the car's position on a desired position on the beam by adjusting its tilt via servo motor. The system incorporates a sonar sensor to measure the car's position, translating the data into actionable feedback. A PID controller minimizes deviations from the desired position and the servo motor is optimized for precise angular control. So this is the setup for the experiment. Here we can see we have used two sonar sensors. The sonar one is the set point sensor that measures the desired position or the set point for the car on the beam. It also provides feedback to the system about where the car should be positioned. Sonar 2 is the position sensor that measures the car's current position on the beam. It supplies feedback to determine the deviation from the set point. The car is the object being balanced or controlled on the beam. Its position is adjusted by tilting the beam. The beam acts as the platform for the car. It tilts to control the movement of the car based on feedback from the sensors. The servo motor controls the angle of the beam. It adjusts the beam's tilt to move the car toward the desired position. Lever arm connects the servo motor to the beam, transfers servo motor's motion to tilt the beam. Object for setting reference is used to manually set or indicate set point position. The process begins with a reference signal representing the desired position of the car on the beam. This reference signal is compared to the boss actual position y in the feedback loop, generating an error signal. This error signal quantifies the deviation of the car's current position from the desired position. The error is fed into a PID controller, which generates a control signal to minimize the error. The PID controller uses three terms to achieve this: the proportional term, the integral term, and the derivative term. The output of the PID controller serves as the input to the motor model, representing a digital servo motor. The motor converts the PID signal into a physical tilt angle theta for the beam. This tilt causes the car to move in the desired direction. The car and beam model describes the behavior of the car in response to the beam's tilt. The relationship between the beam angle theta and the car's movement is governed by the system's physical dynamics, including factors like gravity, inertia, and friction. A feedback loop continuously monitors the car's actual position y and feeds it back to the system for comparison with the reference position. This real-time feedback allows the system to correct any discrepancies by adjusting the beam angle, ensuring the box stabilizes at the desired position over time. The flowchart illustrates the methodology for the car on beam balancing system. It describes how the system calculates the necessary adjustments to keep the car at the set point. The set point is the desired position of the car on the beam as defined by the user or system. This acts as the target input for the control system. Error calculation is the difference between the current position from sonar 2 and the set point from sonar 1. This value indicates how far the car is from the target position. PID controller processes the error using proportional, integral, and derivative terms and produces an output U, which is the desired correction angle in radians. Angle conversion converts U from radians to degrees for compatibility with the servo motor. It ensures the calculated correction is in a usable format for the system. Angle mapping maps the degree angle to the servo motor's operational range, and it ensures that the servo motor's movement corresponds to the required beam tilt for correction. Servo motor adjustment adjusts the servo motor's angle based on the mapped value. The beam tilts accordingly, influencing the car's motion to reduce the error. The car moves to a new position on the beam as a result of the adjustment. The system loops back to measure the new position and recalculate the error. This entire process repeats continuously, creating a closed loop system where the beam's angle is dynamically adjusted to maintain the car at the set point.
Hello, my name is Shomik Shah and the ID is 2006011. I will take the presentation from here on. At first, we need to calculate the set point and the current position of the car. We used sonar sensor for this purpose. A sonar sensor works by emitting ultrasonic waves from a transmitter. The Arduino sends a signal to the sensor trigger spin for 10 microseconds. This activates the sonar to emit an ultrasonic pulse from its transmitter at a frequency of 40 kHz. When the wave hit an object, they bounce back toward the sensor. The sensor's echo pin detects the reflected wave using the ultrasonic receiver, and the Arduino measures the time and records it as the pulse width on the echo pin. The distance of the object is calculated using the speed of the sound in the air, which is approximately 0.034 cm per microsecond, and the distance is given by this equation. Here, division by 2 accounts for the round trip of the ultrasonic wave. Using the values, we have the simplified equation for distance, which is given by this. Here, we took 50 samples to reduce the noisy data. By averaging the samples, it improves the accuracy of the distance measurement. Then the error is calculated using the set point and the current position of the car. The error is inputted into the PID controller. The PID controller gives us an radian angle U as the output, which relate the error to an angle. Then the radian angle is converted to the degree angle. The saturation check in the PID controller algorithm is necessary to ensure the control action U stays within the physical limits of the system. So we have to define Umax or Umin, and Umax and Umin for radians also. For our system, we have considered the range of minus 0.524 to plus 0.524, which is basically minus 30 degree to plus 30 degree. These max and min values were calculated by observing the values of U for limiting cases where the error was maximum. If U goes below the U minimum, it is set to U minimum and the saturation flag is enabled. Similar action is also taken for the case of U max also. This prevents the instability or the breaking of the setup. Also, by enabling the saturation flag, we prevent further accumulation of the integral term until the control output returns within bounds. Because if the integral term continues to go unchecked, it might cause integral windup. Now, U degree is mapped to a new range of values that are appropriate for the system physical constraints. The equilibrium position of the servo corresponds to the angle of 90 degree. To move the car to the leftmost position, the servo angle needs to adjust to 130 degree, while to move the car to the rightmost position, the servo needs to adjust to 60 degree. So we need to map U degree to this range. We use the map function for this purpose. The map function performs a linear transformation. Doing the calculation, we get the equation for this linear transformation, which is given by this. The following graph shows the relation between the U radian and the angle. As the U exceeds the maximum or minimum range, the servo angle is set to maximum of 130 degree and 60 degree respectively. This wraps up my part of the presentation. My project mate will take on from here. Thank you.
Hello, I'm Nityananda Bishwas, ID 2006025, and I'll take the presentation from here. Previously, we explored how the PID controller works. To make it perform effectively, we use Ziegler-Nichols method to find the coefficients Kp, Ki, and Kd. To perform Ziegler-Nichols method, we first set Ki and Kd equal to 0 and increase Kp gradually to see for which Kp value we get a sustained sinusoidal response like this one. So in our case, we have seen that this Kp value is 12, which is called the ultimate gain. And this is 12, and the period is 4.5 seconds. And using these equations, we have calculated the values of Kp, which is 8.4, Ki, which is 3.73, and Kd, which is 4.725. This part of the control system adjusts servo angle based on the error between the ball's position and the set point. The logic ensures smooth and adaptive control by varying the step sizes based on the error magnitude. If the error is moderate, like if it is between 0.35 centimeters and 3 centimeters, the current angle is adjusted in steps of 3 degrees. This is done to make sure the system stays stable and overshoot is avoided. If the error is larger, like if it is above 3 centimeters, the current angle is adjusted in steps of 5 degrees. This is done to give a quicker correction to the whole system. And if the current angle is equal to the target angle, the servo holds its position without any further adjustment. In the car and beam balancing system, specific logic addresses cases where the car is stuck outside the acceptable range for above 3 seconds. This acceptable range is actually plus minus 10% of the set point. If a car is stuck, then we have designed a stack mechanism under which there are two corrective actions. Through these two actions, a car can be taken out of its stuck position. If the car is stuck below the set point, the servo adjusts to 40 degrees drastically, tilting the beam downward to encourage movement to the car. If the car is stuck above the set point, the servo adjusts to 140 degree, tilting the beam upward for the correction. If the car returns to the range within 3 seconds, the system considers uh, the system timer is reset, clearing the stuck condition. So that's all from my part. My group mate will continue the presentation from here. Thank you.
Assalamualaikum. I am Adi Brahman. My ID is 24. So now we'll represent the system as a combination of transfer functions. Since we do our calculations in Laplace domain in the form of transfer functions, we need to represent the characteristics of our physical system in a mathematical form. This is called system modeling. Let us first consider the behavior of the car. Since we have to control the position of the car by changing the gravitational force along its path, we need the transfer function that relates its position to the force on it. This combination of force depends on the beam angle θ1, the gear angle θ2, and the offset of the lever from the rotary point given by delta. So we can write this set of equations. The total force on the car along the beam is the perpendicular component of the gravitational force, which should equal the force causing acceleration and the frictional force. The construction of the apparatus also dictates this geometric constant, which you can use to simplify the relation and directly relate the car's position to the gear angle θ2, the angle of the motor's rotary arm. The beam and offset lengths are known parameters, as well as the mass of the car. For the friction coefficient, we assumed a typical value for wood. Using these values, we have the final transfer function for the car's position, a second order system denoted GB, as you can see on screen. As for the motor, we used one with model MG995R. Note that these DC motors can be modeled as first order systems K by 1 plus tau S. So we need to determine two parameters, tau, which is the time constant, and K, which is the steady state gain. Now the time constant is only 1/4 of the rise time, which you can get from the specifications to be 0.16 volts, 16 seconds at 6 volts. So tau should equal 1/4 of that, that is 0.04. And the steady state gain for the motor is the ratio of change in output to the change in input. Since the motor is PWM controlled, input is the pulse width and the output is the rotational angle. Again, from the specifications, we see that a change of 0.33 milliseconds, that is here from 1.33 seconds to 1.66 seconds, the change in output is 60 degrees, that is, it goes from 60 degree to 120 degree. So we get the gain coefficient K equals that change in output by change in input. So K turns out to be about 182. Using these two values, we can write the final transfer function for the DC servo motor here. So now that our modeling is done, the rest of the presentation, another project member will take over. Thank you.
Hello, my name is Aditya Dipro, ID 2006018, and I am starting my part of the presentation now. Here we can see the Simulink model of our whole system. At first, we are setting a reference point, which is our final position of the car that is fixed from our first sonar sensor. Then we are taking current position of the car as feedback from second sonar sensor. Then we calculate the difference of the reference and current position of the car and calculate the error signal. This error signal is then given input to the PID controller, and this PID controller gives a radian angle as output. Here Kp and Ki's values are calculated from Ziegler-Nichols method, and the Kd's value is changed somewhat for better response. The output of the PID controller is a radian angle, which is then converted into degree angle. Then, as we saw earlier, we need to map this angle to the servo angle, and this mapping is done through a linear equation whose gain is 7/6 and offset is 95 degree. So after mapping this angle, we are giving this angle as input to the servo motor, whose transfer function is written here. and then this angle is given input to the beam whose transfer function is written here. By continuing this process and taking feedback again and again, the servo fixes the position of the card to our desired reference point. Now for system identification, we use MATLAB's system identification toolbox, and for this we are exciting the whole system with the step input, and then with the step response we are approximating the transfer function of the system. Here at first we are calculating TH, which finds the average time interval which serves as the sampling time TS. The iData function in MATLAB is used to create a dataset for system identification. This dataset contains input and output data along with the sampling time. The TFS function in MATLAB is used to estimate a transfer function model from given input-output data. TFS applies numerical algorithms to identify the best fit transfer function and approximates the behavior of a system. Here we used 3-step response from our real-time system and used them to approximate transfer functions. For the first step response, we can see that the transfer function has 5 poles and 4 zeros, and the transfer function is written here. Here the blue line shows the step response of our estimated transfer function, and the gray line shows the real-time step response of our whole system. Its fit is almost 89%, and its MSE, mean square error, and FPE, final prediction error, are written here. Here the second transfer function which was estimated from our second step response is written here. Again we can see that here the number of poles are 5 and the number of zeros are 4. Here fit to estimation data is 91.33%. Here FPE and MSE's values are written here. And for the third step response, we can see the transfer function written here, and here again we can see the number of poles are 5 and number of zeros are 4, and here fit to estimation data is 93.05%, and FP and MS's values are written here. We can say we got 5 poles and 4 zeros for all transfer functions, but the coefficients are not same for all transfer functions. We can surely say our whole system has 5 poles and 4 zeros. Here the coefficients are different because of non-linear dynamics and disturbances for our system. And that's all for my part. From here on, one of my teammates will take over. Thank you.
Assalamu alaikum everyone. I am Ashik Shariar. My student ID is 2006026, and now I am presenting the demonstration video of our project. আচ্ছা, আমরা গ্রুপ 3 আমরা এখন কন্ট্রোল প্রজেক্টের ডেমনস্ট্রেশনটা দেখব। আমাদের প্রজেক্ট হচ্ছে অবজেক্ট ব্যালেন্সিং অন এ বিম ইউজিং এ পিআইডি কন্ট্রোলার। তো বেসিক্যালি আমাদের এইখানে হচ্ছে একটা রেফারেন্স পয়েন্টে আমরা আমাদের এই কারটাকে ব্যালেন্স করার চেষ্টা করব। আমাদের রেফারেন্স পয়েন্টের জন্য আমাদের কাছে এই সোনারটা আছে। এই সোনারের সামনে আমরা এই অবজেক্টটা রেখে যখন আমাদের কোডটাকে রান দিব তখন সে হচ্ছে আমাদের রেফারেন্স পয়েন্টটাকে সেট করে নেবে, এবং এরপরে আমাদের এই গাড়িটা সেই অনুযায়ী আমাদের এখানে ব্যালেন্স হবে আর কি। তো আমাদের এখানে দুইটা স্কেল দেয়া আছে। তো আমাদের সোনারের ভ্যালুটা আসলে স্কেল অনুযায়ী একটু 19-20 হতে পারে। তো আমরা এই ভ্যালুটা চেক করার জন্য আসলে আরডুইনোর আইডিইতে সিরিয়াল মনিটরের এই ভ্যালুগুলো চেক করব। তো আমি শুরুতে এটাকে এখানে রেখে কোডটাকে যদি আপলোড করি, শুরু করো। আচ্ছা, আমরা this is our test case 1. Test case 1. রেফারেন্স পয়েন্টটা দেখতে পাচ্ছি, এটা হচ্ছে 9.72, আর এটা এখন আমাদের সেট হয়েছে হচ্ছে 9.66 আর কি। আমাদের এররটা দেওয়া আছে 0.03 সেন্টিমিটার আর কি, বা এই সেই অনুযায়ী আর কি এখানে আমাদের এটা মিলে গেছে। This is our test case 2. আমাদের টেস্ট কেস 2 যেটা আমরা এখন দেখব। এখানে হচ্ছে আমাদের রেফারেন্স পয়েন্টটা সেট ছিল হচ্ছে 18.71 এ, আমাদের এটা সেট হয়েছে হচ্ছে 18.6 বা 5 এর আর কি। It is our test case 3. এখানে হচ্ছে আমাদের রেফারেন্স ছিল 5.44 আর এটা সেট হয়েছে 5.25 আর কি। Let's discuss about the main challenges of our project. Initially, we planned our project as balancing a ball on the beam, but here we used the sonar sensor as to distance the measure, but the sensor HCSR04 works at line of sight, and the ball shape is circular, or I mean spherical. That's why the sonar sensor output data was really hard to capture. Here in this plot we can see the distance sonar sensor distance with the ball. That's why we took another object, a car, and to get the accurate result from the sonar sensor we used a board to measure the accurate distance here. The another challenge was the servo response time was slow. That's why the car here was getting hit on the sensor, and the sonar sensor threshold distance is from 2 centimeter to 200 centimeter. If the object gets too close from the sensor, then it can't be able to measure the distance. That's why we used an obstacle to get the minimum threshold distance for the sensor. Then another challenge was the we used the beam which was not as long. If we can use a longer beam, about 40 centimeter, it will work better in the case, and using another servo which has a better response time which will work good for our project. And here are the references of our project, and thank you so much for hearing this presentation.